Hello, this is iMathit with Samuel, okay? And in today's lesson, I am going to be showing you how to obtain the integrating factor to solve differential equation of this type. So when you see a differential equation that looks like this, it seems like an exact differential equation, but when you carry out for the test for exactness, it fails, and you are going to need other method to solve the differential equation. So, well, let's carry out the test for exactness for this particular one. So, for a differential equation to be exact, so the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. So, in this case, we set m is equal to negative 2xy minus 3y squared, right? And n is equal to x raised to power 2 plus 2xy, right? So those are the m and n respectively. So you probably remember that generally a differential equation is of the form m dx plus n dy, and that is how I set m and n respectively. So let us go on and obtain the partial derivative of m with respect to y. So m is negative 2xy and minus 3y squared, right? So what is the partial derivative for 2xy? So since we are finding the derivative with respect to y, so that will be negative 2x, that's the constant there. And for negative 3y squared, that will be negative 6y, right? So what's the partial derivative of n with respect to x? So that is going to be 2x and plus 2y, right? So in that case, 2y is a constant, right? So you will see that these are not equal. So the test for exactness failed. So we are going to need another method to solve this type of differential equation. So if we can get a function, okay, that will be introduced into this equation, so that will make this equation exact, we can continue and go on solving this problem using the exact method. So the function that can be introduced here that will make this exact is called the integrating factor. Now this integrating factor can be a function of x. So there is a function of y as well that can serve the same purpose, and even a function of x and y. So these functions exist that can serve as the integrating factor for this function. Well, it might be difficult to obtain some of them. So if you hit a plateau as you attempt to find either any of this function, just try to find another if it's difficult. Okay. So if you cannot solve your problem, then solve another easier one. So so I am going to assume it's a function of x. Okay. So let's assume the integrating factor required to make this differential equation exact is a function of s. So that's why I'm multiplying the equation by a function of s. And when I do that, so I will be having f of x multiplied by negative 2xy, so and minus 3y squared dx, and plus f of x multiplied by multiplied by x raised to power 2 and plus 2xy dy. Okay, if I multiply that, and if I multiplied f of x by 0, it gives me 0, right? So now this is a new differential equation we have to deal with. Our m has changed and our n has changed as well, having the integrating factor f of x in it. So I will assume that this is exact now. Now, how do we know this is exact? We usually carry out the test for exactness, right? And actually, what we are trying to do now is not actually carrying out tests for exactness. Instead, we are using this knowledge to our advantage. So a differential equation will be exact if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to s. So let us check that statement here. So we are trying to use this knowledge to our advantage. Not actually, we are not interested in just the test. Okay? So let's do that. So when we find the derivative of m with respect to y, partial derivative, f of x is going to be a constant, right? Because it does not have the constant function y in it. So we have negative 2xy minus 3y squared to differentiate. So and that will be negative 2s minus 6y, right? So this should be equal to the partial derivative of n with respect to s. Now, this is a product function, right? So you take the derivative of f of x, right? You leave s raised to power 2 plus 2xy alone, right? Then you add it to, then this time you leave f of x alone, and you take the derivative of s raised to power 2 plus 2xy. And that's going to be 2x plus 2y, right? So if we can just solve this equation and obtain f of x, then what we obtain is going to be our integrating factor. So let us see if we will be able to do that. So I'm bringing f of x component with f of x on one side, okay, and then I would have this. Please, if you are getting value from this lesson, remember to hit the like button and subscribe to this channel for more educational content like this, math lesson like this. So okay, so at this point, what would you do? The next thing to do now is to factor f of x, right, off here. But do not forget that negative in between there, right? So we'll have f of x into negative 2x and minus 6y and minus 2x, right? And minus 2y. Do not make mistake there. So and that's equal to f prime of x multiplied by s raised to power 2 plus 2sy. So when we put what we have on the left hand side together, we have f of x into negative 4s and minus 8y equals f prime of x into multiplied by s raised to power 2 plus 2xy. Okay, so I think we did not hit a plateau here. If this will be too difficult for you to continue, you are going to know at this point. So if you notice that it's too difficult for you to continue at this point, so I suggest you simply go on and try f of y. Okay, so when I clean things up a bit, I have f prime of x all over f of s equals to negative 4s minus 8y all over s squared plus 2xy. So let us factor what we have on the right hand side there. You will notice that that fraction can be factorized, right? So we can factor it. At the numerator, we can factor negative 4, right? So and we'll have x plus 2y in there. Please note that is x plus 2y, please. And at the denominator, we factor x. So we have f prime of x all over f of x is equal to negative 4 all over x. Wow. So what would you do at this point? The next thing is we integrate both sides, right? So with respect to x, because we have functions of s all over the place, right? So what's the integral of f prime of s all over f of s? This can be a little bit tricky, but actually it's a simple one. So that's going to be ln of f of s. You know that, how would you explain that? So the derivative of ln of f of x is going to be 1 over f of x and multiplied by the derivative of f of x. So which is what you have in this integral. So we are certain that this is correct. While on this side, I bring out the constant, negative 4, and the integral of 1 over s is ln of x, right? So do not put in the constant of integration here, because we are just trying to find the integrating factor. So at this point, I used the rule of logarithm there to rewrite that in that form, and taking the exponent of both sides, there we have it. F of s is equal to s raised to power negative 4. So we just need to put this s raised to power negative 4, the integrating factor, back in the original differential equation. Then it will be a SAT this time, and we can go on and complete the process and find the general solution. So let us do that. So when we put s raised to power negative 4 back in, we have s raised to power 4 multiplied by negative 2xy minus 3y raised to power 2 dx, and plus x raised to power 4 and multiplied by x raised to power 3 plus multiply s raised to power 3 plus 2xy dy. Okay, so and this is equal to 0. So what's next? Okay, let me open the bracket here. So when we open the bracket there, we have negative 2 x raised to power negative 3y and minus 3x raised to power negative 4 y raised to power 2 dx, and plus x raised to power negative 2, right? And plus 2x raised to power negative 3 and multiplied by y dy equals 0. So at this point, we have another differential equation to deal with. The m here have changed and n as well. So we don't need to carry out test for exactness no more, because we are certain what we introduce here will make this exact already. But for the sake of practice, let's go on and carry out the test, okay? So what's partial m partial y? So you know that's going to be negative x raised to power negative 3, right? Y is a constant. Well, y will be derivative of y is 1, right? And minus 6x raised to power negative 4y. The partial derivative for n with respect to s is going to be negative 2x, right? Raised to power negative 2 minus 1, which is minus 3, right? And minus 3 times 2 is negative 6, right? And x raised to power negative 4, and y is a constant multiplied by y, right? So if you look at this, you see that these are equal to each other, right? So we know that the differential equation is exact. So we can now go on and use the exact method. And to use this method, you set a function u, which is the original function that yields the differential equation, and it will be equal to the integral of m with respect to s and plus k, where k is not a constant of integration but a function of y that best completes the function u. So this would mean integral of negative 2x raised to power minus 3y minus 3x raised to power negative 4y squared dx and plus k. So what is this integral? Let's evaluate this integral with respect to x. So for negative 2x raised to power negative 3y, that will be minus 2x raised to power minus 2y and all over minus 2, right? Good. And this would be minus 3x raised to power minus 3y squared all over minus 3, right? Minus 4 plus 1 is minus 3 and plus k. So and those cancel out, right? So what do we have left of u? Okay, so our u of s comma y, u, the original function that yields this differential equation, is going to be x raised to power negative 2y plus s raised to power negative 3 y raised to power 2 plus k. Now we need to find k. So to find k, let us differentiate u with respect to y, okay? I meant the derivative of u with respect to y. What is it? So to get understanding total differential is the key to understanding exact differential equation, the method here, because we are working total differential backward, okay? So because what we have been doing right now is solving the exact differential equation. So when we differentiate u, we find this, we obtain this. And what is n? So n is x raised to power 2 and plus 2x raised to power negative 3y and plus nothing, right? So we say plus 0. Now by comparison, you see that the k dy is equal to 0. So I hope you agree with that. So like I said, understanding total differential is the key to understanding this. So we we integrate and we obtain k is equal to c. And there we have it. So the function u of s comma y, which is the general solution for the differential equation, is s raised to power negative 2y and plus s raised to power negative 3y squared equals c. And this is solution to the differential equation. Well, please hit the like button and subscribe to this channel for more educational content like this. Now in the next lesson, we will be solving this problem up here, and we are going to be having an initial value to deal with so that we find specific solution. Well, until next time, keep mathing it and keep winning.